Hey everyone, Steve with Off-Grid 48. Welcome back to the Wood Gasifier Builders Workshop. So today we're going to go through and review the Peterson gasifier design, and I want to show you a couple different options that you've got for connecting the heat exchange to the cooling system and dealing with the hot gases that are generated in the wood gasifier. So we're going to walk through that. But before we get to that point, I want to thank everybody who's subscribed to the channel and have provided me with good positive feedback. I really appreciate that on all the videos, and hopefully all the videos that we put out on building this gasifier has helped a lot of people get a good quality gasifier. For those of you that might be new, that haven't subscribed, I encourage you to go ahead and subscribe to the channel. I think there's a lot of good information, a lot of detailed information about building this wood gasifier. Far more than you can just learn in a single book or single reference. So feel free to subscribe and look at all the other videos that we've got about this gasifier. So before we get into the details about the heat exchange transfer into the cooling system, I want to take a few minutes and kind of review the gasifier design, the flow of the gas, and how the whole system works, and then we'll kind of get into the details. Okay, so this is the Peterson gasifier design, and it's a cutaway. So you can see here in this first tank, I've got the reactor tank. Attached to it, I've got what we call the heat exchange. Then this tank here on the side is the filtration tank. And in the back, you see here coming out of the heat exchange, I've got the cooling assembly, comes down here, and then I've got the condensate tube, which collects the condensate that comes out of the gas, goes into the filtration tank. The gas rises up through multi-stage filter and comes out the gas exit port for whatever application you're using. So whether it's heating, cooking, or fuel for a generator or a vehicle application. Okay, so that's the main design, and those of you that may be familiar with the Peterson design know that this design is about 10 years old. He published his book in about 2014, and I've been spending the last 8 years or so working on building the gasifier, but correcting. There's a lot of issues in the original design, some safety issues, some building issues, some mistakes on measurements and things like that. And then we've added a series of enhancements to it, so to both the gasifier itself and to the actual build process. But I want to kind of review the basic operation of the gasifier is still the same, but I want to kind of review some of these enhancements and also talk about how the gas is created and the gas flow, and then specifically in this video, options that you have for taking the hot gas that's created coming out of the heat exchange goes into the cooling assembly, because there's been some discussion about that. So in looking at the gasifier design in the reactor tank, this is where the fuel is stored, and this is where the combustion takes place. So the lid comes off, the fuel goes in. We start down here with a layer of charcoal, and then we can add raw wood chunks on top of it. But down here in the combustion zone, this is where the air jets are. This is where combustion takes place. This is where the high temperatures are reached. So during combustion, temperatures reach 2,000, maybe in excess of 2,000 degrees. It takes that charcoal, breaks it down into its basic components of carbon and gas, and then that falls down into the reduction tube where basically the gas is actually created. The grate will catch the activated charcoal that's left over from that process. Then the gas flows down through over to the heat exchange. It comes up into the heat exchange, and then it is diverted and circulates around the reactor on what's called the pyrolysis layer. So the layer directly above the combustion chamber is where the raw fuel is. We're circulating the hot gas around that, so we're drying it out and turning basically that raw wood into charcoal, so as it falls down into the combustion chamber, it's ready to be burned. And then it comes around and exits. I'll turn this around here. It exits the heat exchange right here, and then you can either go up. The original design has the exit going vertically into the cooling system. We've changed that to make it a horizontal connection here, but basically it's the same thing. The gas flows out of the heat exchange into the cooling assembly, and then the cooling assembly starts cooling that gas, and any condensate in it is going to be collecting down here in the condensate tube, and then that gas further cools down, enters the filter tank, rises up through a filter basket that's got multi-stages of filtration. I'll turn this back around. It comes up, rises. There's a filter basket in here that's got filter media. The gas rises up through multi-levels of filtration, comes out the gas exit, and then from there we can use it, directly burn the gas, or use it as fuel for a generator or for a vehicle. Okay, this is where the blower is that creates the suction to pull the air in and then pull the gas through the system. So if you're not familiar with the original Peterson design in his book, basically all of this in the original design is one big welded component. So if you have an issue with any piece of it, the heat exchange, the reactor, the cooling assembly, anything, you have to cut it apart to address that. Or if you want to change configurations, you have to cut it apart to do that. One of the first enhancements that we made is we took this and we made it modular. So now the reactor and the heat exchange is one subassembly, the base is one subassembly, cooling tubes are one assembly, condensate, and so on. So this helps from several different reasons. One, it's easier to build that way. I can build the sub-assemblies in any order that I want. I don't have to follow his order that he lays out in his design. And it makes it easier because that way I can work on each sub-assembly separate and then put them together and then get the whole unit. So when you do that, though, we got to account for that gas that's flowing through the system, and then as these sub-assemblies connect to each other. So one of the issues that came up is, the hot gas passing between the heat exchange and into the cooling. And I've actually got a couple videos out that talk about that more. When we were doing this, I said I've been doing it about 8 years. It's interesting to note that basically Ben Peterson, he 100% endorsed all of my enhancements for about 6 years. 6 of the 8 years that we've been doing this, he's wholeheartedly endorsed. And it wasn't until the last couple of years that we had a falling out that he all of a sudden changed his mind and decided that he didn't like these enhancements, and he tried to raise some fear in the public about the method that we use to connect the heat exchange to the cooling assembly. So I want to kind of go through that. But first, let's talk about the gas when it's created. So the heat that's created in the combustion area, like I said, it's the hottest. Like I said 2,000 to 2,500 degrees. And that's really a function of the air that's being pulled in. If I'll use the example of a generator. And the generator or any engine provides suction. A smaller generator obviously is going to provide less suction than a big engine. So the more suction, the more air that's coming into the system, the hotter the combustion zone will be and the hotter the resulting gas. But generally the combustion area is going to be in that 2 to 2,400 degree Fahrenheit area. But then once it drops down into the reduction tube and the gas is created, the gas itself that's created, again, it will vary in temperature depending on the amount of suction that's coming in. But typically, the gas temperature when it's created is going to be in the 600 to 800 degree range. That's when the gas is created, okay? Then, from that point, as we start to move the gas into the heat exchange and around and through the system, the gas cools very, very quickly. And so by the time it makes its way through the whole system, filtration, and comes out the exit port, the gas is actually cool to the touch. So we might be starting with a temperature of 2,400 degrees, but coming out the exit port here, it's cool to the touch, is 60, 70 degrees on the gas. Okay, so specifically, what I wanted to talk about is where that gas is the first time that we connect two sub-assemblies, the reactor and the heat exchange, to the cooling. Okay, if I'll turn this back around again to see, that's where the gas comes out of the heat exchange and enters the cooling assembly. So between that, we have to have a connection. And what we've been using very effectively since I started this enhancement is we've been using these high-performance silicone adapters. Now, this is a HPS, high-performance silicone. This orange colored silicone is rated at about 500 degrees. Okay, so we use that at the hottest point here. But we also have several other connection points where we're going from the cooling assembly to the condensate, from the condensate into the filtration, from the filtration out to the gas exit. So we have several other points that when the gas flows through that we use. And as I said, the gas is cooling down very, very quickly. So we haven't seen the need that we need to use a high performance silicone adapter that's rated at 500 degrees all the way through. We use these black ones that are rated a little bit lower. These are rated at about 350 degrees. And we put those on the subsequent other connections for the gas exit. Now, obviously, if you're running a very, very large engine and you're measuring gas temperatures and they are very high, you could still use this throughout the system. You have that option. In our experience, and we've made, just a lot of these builds and kits, I've never had one of these fail. I've never had one of these black silicone connectors fail. So in my opinion, the gas cools down sufficiently that we only needed one of these at the gas exit from the heat exchange to the cooling, and then the rest of the time, a black silicone adapter works very well. So let's talk a little bit about the heat. So we mentioned that the gas that's created as it leaves the reduction area might be in the 600 to 800 degree range, okay? Now, obviously, if I expose this, even at 500 degrees rating, if I expose that to hot gas that was in excess of 500 degrees, it would melt, okay? But the way that the build in the system is, we never have hot gas come in contact directly with the silicone adapters, okay? We're just using this in-between connection. The connection that actually comes out of the heat exchange that goes into the cooling assembly is a metal-on-metal. Basically what we have is we've got a 2-inch exhaust tube. This is a 16-gauge standard exhaust tube. That's what's coming out of the heat exchange, and that's what the cooling assembly is. So what we end up with is coming out of the heat exchange, going into the cool assembly, we use a standard elbow, again, 16 gauge, and then we connect these two here, and it's going to be a metal-on-metal connection. And then where we're going to put the silicone adapter is we're going to put this on here, connected with, secured with T-clamps. So the hot gas that's passing through here never does come in contact with this. So typically, like I said, if I'm running a generator, let's say 15 kilowatt generator, up to a 15 kilowatt generator, the gas that's passing through it by the time it hits this point has cooled down to below 500 degrees. If I'm running a very large engine, it is very possible that the gas, when it reaches this point, is in excess of 500 degrees. But the hot gas never touches the silicone adapter. We have what we call heat dissipation, right? So the hot gas that's flowing inside the tube, we have on the outside, the gas temperature is quickly dissipating. And we've done a lot of testing on this. We've had sensors measuring the gas as it flows through. We've had sensors measuring the outside temperature. And basically what we found is that the temperature of the gas coming through, the outside temperature of the metal is about almost 50% less. So if gas is coming through here at 500 degrees, the gas on the temperature on the outside of this is around 250. So for the temperature on the outside of this to reach 500 degrees, the gas inside would have to be close to 1,000 degrees. And I've never, in all the testing that we've done, I've never measured the gas at 1,000 degrees. But that's what would have to happen. The gas would have to be at about 1,000, and then the temperature's dissipated through the metal, and then this would be on the outside. So that's just to kind of give you an idea. In our kits, and we've been selling these for years, we include both these high temperature silicone, and then we enclose the lower temperature ones. And in all those years and all the kits and builds that we've done, I've never had one of these fail, and I've never had one of these fail. So, but Ben has tried to make it a safety issue, that he's concerned. Basically, if you go through and look at some of my earlier videos, and he's even got a video out there where he says it's dangerous. It's a lot of hype. He just put it out there because him and I had a falling out, and he's just trying to scare people. But basically, he's saying that this silicone connector is going to fail, it's going to leak carbon monoxide, and you're going to die. But none of that is true. But I have had some questions from people wondering about the validity of using these silicone. So that's another reason that we're doing this video today. So in the kits that we sell and in the builds that we do, I still use these. So this is a very expensive piece of silicone. And like I said, I like it because even if the piece of metal here isn't completely round, it's got some dings in it or whatever, by the time I secure this and put the T-clamp on it, it's going to fill any gaps and secure on there very well. So I really like these. They've done very well. So these are always going to be in the kits, and we use those in the builds. But we recognize that there may be some people out there that have some questions, have some concerns, want to use a very, very large engine, and could potentially exceed the rating on this. So what we've done is, and I put this in my book as well, you can go to your standard auto supply place. This is a 2-inch connector for exhaust tubes. So this is actually cheaper than this. If you don't want to use a silicone, you can use this to clamp the two pieces that I mentioned. Now you'd have to add, because this, basically with this metal on metal seal, if there's any irregularities in this tube, you're going to have to fill that with some kind of a sealant. So what we're recommending, and we're including these in the kits as well, is this Rutland stove and gasket cement. This stuff's rated for about 2,000 degrees. So you can put that in there as an internal seal, put that on, and then now you've got stainless steel fitting between the two metal connectors here. So that's the second option that you have if you're concerned about temperature, if you're concerned about exceeding the temperature on these silicone seals. And then one other option that I've just recently started adding to the kits is I've developed another part here that's basically a flange. And what this is it takes a standard 2-inch tube, and then you would weld this flange on, and you have two flanges, and then you bolt these together. These holes, there's 8 holes here for a 5/16 bolt. So that would mean that coming out of the heat exchange, you would have one nipple. Then coming out of the elbow, you would have another one. And so what it would look like is it would look something like this. So coming out of the heat exchange, we have our flange with 5/16 bolts, 8 of them, and then going into the cooling assembly. So now that's a solid metal on metal. I still recommend, if you're doing this, to go ahead and use the stove and gasket cement inside as a gasket. But basically this should seal any concerns from anybody might have in going at a very high temperature. Even if theoretically the gas was 1,000 degrees, which like I said, I've never seen it, this would still be more than enough for that. So that's the other option that you had. And I just wanted to kind of make that option clear to you. Now we're including this in the kits. So now when you get one of our kits, you'll get a set of these flanges, and you'll still get this and T-clamps. I don't include this, but you can pick this up at an auto parts store very, very cheap. Now, just to give you another idea of kind of what we're talking about here is this is actually the heat exchange. So this piece right here is the box that attaches to the reactor here, okay? So if the reactor was here and the tank was here, then this would be the heat exchange box. The gas would come, basically would leave the reactor, would rise up, and you see I've got this divider plate that goes into the reactor. It forces the gas to come here and go around the reactor, which is the pyrolysis layer that I mentioned. We're extracting the heat from that hot gas to heat the fuel as it drops down in the reactor. Then the gas enters this chamber. This is the exit chamber, and it can either go out vertically. We can come out here like in the original design, or what we've done here recently is we're coming out horizontally and then going into the cooling assembly. So this is just give you an idea. This is what the heat exchange box looks like. And this is a clean out port. So I can open this up, put a shot back in here, and I've got a clean out port on the bottom. So if there is any soot or anything in the gas that gets deposited as it works its way around, these clean out ports are available for you to go in and clean out as well. Okay, so I just wanted to kind of go through that. You have these three options. So you've got the silicone, you've got the stainless steel, and then you've got the new, I'm calling it the heat exchange gas exit flange. And that's all going to be in the kit for those of you. So anyway, so that's basically that. I hope that helps clarify a little bit. You have different options. So again, thanks again, guys, for joining. And also, by the way, I just want to take a minute and thank you. You know, we put out our book a couple of months ago, so now I've got my own book, the Wood Gasifier Builder's Workshop. If you're interested, and matter of fact, in each of the kits now, I'm putting a copy of the book in there. It's got all very detailed instructions. It's got 310 pages over it's color, heavy bond paper. It's got detailed drawings, CAD drawings. It's got everything that you're going to need on building, operating, and maintaining this V3 gasifier, as we're calling it. So that's everything, guys. Thanks again. I appreciate it, and we shall see you on the next one.